Hello everyone. In this video we're going to learn how to find approximations of trigonometric function values using a calculator. Remember that when it comes to any of the special angles that we have learned about so far, which includes basically 30-degree angles, 45 and 60-degree angles, and any angle whose reference angle ends up being those three, so which includes of course all these 9 angles here, also included in the group that we consider to be special are quadrantal angles, 0 degrees, 90, 180, 270, or any angle that happens to be coterminal with them, right? So when it comes to computations of any of these angles, or angles that either have the same reference angle or are coterminal with these angles, we want to give exact values in the methods that we have learned already in the past couple of sections or videos. Now, however, if you have to find the trigonometric function values for an angle that is not included here, we're going to be utilizing a calculator. But do keep in mind, when it comes to any of these, you must always use exact methods in the way that we have already learned. In this video, we'll be looking at calculator approximations of trig function values, of course, for non-special angles. It doesn't, of course, indicate that we can't find the measures for special angles using a calculator. It's just that we would like to use exact methods for those particular ones to strengthen our skills. Calculator approximations of angle measures, and so for this, basically, we're going to be utilizing inverse functions where we're given the sine or cosine or tangent, for example, of an angle, and we're asked to find the angle itself. So this will be taking a preliminary look at inverse trigonometric functions. We'll be going into much deeper analysis later, but we'll just get a preview of inverse trigonometric functions in this video, and then we're going to look at a couple of applications. When it comes to calculator approximations of trigonometric function values, the most important thing to remember is that you must make sure your calculator is in the correct angle mode, because remember that most calculators don't automatically have angle degree measure as the default angle measurement measure. So we have to make sure that we choose that before we proceed. So in our first example, we're going to use a calculator to find the approximate value of the sine of 52 degrees. Of course, 52 is not one of the special angles we've been dealing with. So we are going to go ahead and use a calculator, and we're going to find the answer to the nearest hundredths. So pay attention to all these instructions, please. And we're of course going to make sure the calculator is in degree mode first. So notice that when you do start a calculator, if you go into the settings mode of your calculator, oftentimes you'll find this setting. Whether you're using this or you're using TI-84, it's usually the same scenario. Here we can see the TI-84 window. Notice that in the settings you have the same problem. It's in radian mode. So in both scenarios, you're going to want to go ahead and go to degree mode. So we can go like that on a TI-84, or we can go like so on this HP Prime calculator, for instance. But any calculator that you use, as long as it's scientific, will have these options. Once you choose it, make sure you click in another tab so that the setting takes. Otherwise, it may not become effective if you don't do so. And then you're ready to do calculations, and it'll be in the right mode, right? So we're going to calculate the sine of 52. We don't need to use any kind of degree symbol or anything. It's already in degree mode, so it's going to interpret that as 52 degrees. And there we see the answer. Now, we do want to round it to the nearest hundredths. So to the nearest hundredths, of course, it'll be 0.79 because after the hundredths digit there's an 8, so we need to round up. We add 1 to this 8 and then the rest become 0, so we get approximately 0.78. So we can say that sine of 52 degrees is approximately 0.78, and that's all we really need to do. All right, in this next one we're going to find an approximate value for the cosine of 100 degrees 36 minutes 57 seconds, right? Some calculators can handle degrees, minutes, seconds, but many don't really handle them, or if they do, it's not a very easy setting to get to. So the safest way to fly is to do the following. Just go ahead and type your cosine, and you can go ahead and convert this to pure degrees on the fly. So you already know how to do this. So we're just going to type 100 plus, we're going to turn the 36 minutes into degrees by dividing by 60, and we're going to turn the 57 seconds into degrees by dividing by 3600, just like that. So now you can just hit enter and you'll have your answer. This time we want to round to the nearest thousandths, right? So we're going to get negative 0.184 because the thousandths digit is the 4, which is followed by a 2, so we can just keep the 4 and drop the rest. So approximately negative 0.184. And that is the cosine of 100 degrees 36 minutes 57 seconds. And remember, that's an approximation, it's not an exact answer. So of course, even though we're using a calculator, we should never abandon common sense, right? We should see if this negative answer makes sense. So let's take a look at a graphic of the situation. Okay, so notice that 100 degrees 36 minutes 57 seconds is going to be somewhere in the second quadrant, right? Because we know up to here we're at 90 degrees and here we would be at 180, so it's somewhere in here, and it's actually close to 90 degrees, not that far away, right? So remember what so we'll be looking at, if let's say we draw the angle in this manner, right? We'll be looking at an angle whose terminal sides is has a point on it with coordinates that are negative for the x and positive for the y, right? So therefore, since cosine of an angle is x over r, and we know that the x value here is negative, and r of course is always positive, so we get negative over positive, which is negative. So we expect a 100 degree 37 minute 57 second angle to have a negative cosine, as is obvious from our result, okay? But we did expect it. So this way, when you use your common sense and you're always aware of what you're doing and not just punching stuff into a calculator, then if you do make an error, such as forget to check the angle mode, etc., and an answer comes up that makes no sense, you'll catch it. Whereas if you're just in autopilot mode and you just punch numbers in like a computer, then you won't be able to catch it. When mistakes are made on the computer, it's not the computer that makes them, it's the human being that's not paying attention that makes them, right? So be very careful with your work. All right, so for the next problem, we're going to find an approximate value for the secant of 92.97 degree angle. So notice that, and we're going to round to the nearest thousandths again. So notice on the calculator, there is no secant button, right? So we have to do a little bit of work first. Now notice that secant of 92.97 degrees is going to be, you have to use an identity. You need to know your fundamental identities so that you can use them effortlessly. You don't want to have to go back and do a bunch of searching and digging every time, right? So the problem with students is that in mathematics they memorize what they shouldn't, such as specific problems, and they do not memorize what they should memorize, which is precisely the basic fundamental rules that you'll be using over and over again. Those should be memorized because you'll be visiting them often and you want to be very comfortable with them. So for example, we know from our reciprocal identities that secant of theta equals 1 over cosine theta. So here we're going to say that's equal to 1 over the cosine of 92.97 degrees. So all we have to do on our calculator is go ahead and compute that. So let me clear this a little bit. So we're just going to do 1 divided by cosine of 92.97. Okay, so there it is. So negative 19 point, now remember we're going to the nearest thousandths, and the thousandths digit here is the 0 right there, so it's followed by a 1, so we can just go ahead and drop all that, so it'll be approximately negative 19.300. And that's basically all you have to do here. So make sure that you know how to handle a scenario like that with a function which is not on the calculator using an identity, and we should be in good shape. For the next problem, we're going to use a calculator to find the approximate value of the cotangent of a 53.9 degree angle. And again, we have the same situation where this function is not directly on most calculators, pretty much on all calculators. So what we're going to do is we're going to do a little bit of algebra first. We know that cotangent of 53.9 degrees should be the same as the reciprocal of the tangent, so we get 1 over tangent of 53.9 degrees. If you remember, cotangent of theta equals 1 over tangent of theta, and vice versa. Tangent of theta is also 1 over cotangent of theta. Okay, so the fact is that tangent of theta times cotangent of theta equals 1, right? So you can go ahead and solve this particular equation for either tangent or cotangent, and you'll get either this result or this result, right? So now what we're going to do on a calculator is we're going to type 1 divided by tangent of 53.9. Now remember, you always want to make sure you're in degree mode, but since I've already changed it to degree mode and it's not going to change on its own back to radians unless I tell it to do so, I don't need to check it every time. But when you first start to do some work on a calculator, make sure you have checked it. So that's why I always put this reminder for you at in these problems while we're doing the lesson. So here we're going to the nearest hundredths, so we get approximately 0.73. And that's all there is to that one. All right, so this one is just a sign of a negative number. Makes no difference, we handle it the same way. So we just type in sine of negative 259. So we get 0.98, right? Let's take a quick look, see if it makes sense to the nearest hundredths, of course, right? Approximately 0.98. So Just a quick common sense check, right? Let's go ahead and bring our unit circle back. All right, so notice that for a negative 259 degree angle, we start here and we start moving in a clockwise manner, right? We know that that's going to be negative 90 degrees, negative 180. If I go all the way here, that'll be negative 270. So negative 259 is somewhere in here. It's a second quadrant angle, meaning the terminal side of the angle is in the second quadrant. So we know that in this quadrant, we're dealing with a negative positive situation. So x is negative, y is positive. So the sine of negative 259 degrees, which is y over r of course always positive, is going to be positive over positive, which should be positive because the y value is positive. So we expected a positive sine value for negative 259 degrees anyway, right? And that is what we need to do there. So now, in this next problem, we are going to go ahead and punch this into a calculator just so we can get comfortable with how to do squares, etc. But I hope that you know the answer to this before you even type it in, right? Remember our most important Pythagorean identity. The first one we did, sine squared theta plus cosine squared theta equals what? I think I heard you say 1, right? Yeah, you were right. All right, so as long as this angle is the same and you're finding the sine squared of the angle and adding it to the cosine squared of the angle, you should get 1. Let's go ahead and type it into a calculator though, just to get comfortable with how we handle squares, right? So basically what you're going to do is the following on any calculator. I'm showing you on this. This is a great calculator, and HP generously releases this in a free manner, which you can obtain as well. But for example, on many of our tests, we'll be using class calc, which you'll want to get comfortable with as well, and that, you know, works in a similar manner. All right, so we're going to go ahead. A lot of modern calculators are basically what we call WYSIWYG. What you see is what you get. So you basically kind of type the problem in as you see it, except here with these, what I recommend you do is just go ahead and type the sine of 38.7, get out of those parentheses and then square it like that, okay? And then now we're going to do the same thing with cosine. So we're going to go cosine of 38.7, and we're going to go ahead and exit. We're going to square it, and now we're going to go ahead and just hit enter, okay? And of course we knew that we should get that already, right? So this is a nice confirmation of what we already knew. All right, so now we're going to take a quick look at inverse trigonometric functions, but not in the most detailed manner, just a preliminary look. We'll be doing a very detailed analysis of inverse trigonometric functions later. In this lesson, just at the level of being able to use a calculator to obtain some results. All right, before we go there, we should do a quick review of what an inverse function is. Remember that certain functions in mathematics which are reversible have an inverse, right? So for example, suppose I look at a simple function, right, such as f that sends the letter a to 1, the letter b to the number 2, and the letter c to the number 3. Right? Notice that this particular function is what we call one-to-one. Not only does each input have only one output, but no two inputs have the same output either. This one-to-one aspect of this function makes it reversible. So in other words, given a one-to-one function like that, I can define an inverse function, which we write in this manner, this is not this notation is not an exponential notation. This is a different usage of that notation. What it indicates is the inverse of the function f. So you don't want to read this as f to the power of -1 or f to the -1. When you see this, you want to read f inverse, like so. So notice we can set up an inverse function which sends 1 to A, 2 to B, and 3 to C. So in other words, you start with some input x, you apply the function f to it, right? You get some output y, and then what f inverse does is if you apply it to the output y, it'll send you back to x, right? So in other words, f of x equals y is equivalent to, or if and only if, f inverse of y equals x, right? So they have this relationship with respect to one another, inverse functions, right? You start with one input, apply the one function, you get the output, and then the other function will bring you back to the input you started with. Or you can start with y, apply f inverse, that takes you to x. Then if you apply f, that takes you back to y, right? So it's a mutual relationship. Now, with inverse trigonometric functions, the same situation holds. Suppose that you have the sine of theta equals some answer, right? Notice that what this indicates is that the inverse sine of that answer should be the angle you started with, right? So this relationship is what we need to understand when we apply the inverse function on a calculator. So we'll be dealing with, you know, the domains and ranges involved and all that. So all the real technical details or theoretical details later. But just understanding this basic relationship will suffice for this point in time. Okay, let's recall what we just said. We said if the sine of theta equals A, this is equivalent to saying that the inverse sine of A should equal to theta. So remember, the inverse sine of A, that means is going to be the angle whose sine is A, right? So this is the angle whose sine is A. So it has to be a particular in a particular range, etc. But again, we'll get into those theoretical details later. So since sine of theta equals this answer, that means, now remember, this is playing the role of A, right? So that means the inverse sine of this number, 0.95237612, should be the angle theta that we're looking for. See, make sure this, what we just did here, makes sense to you according to this relationship between the sine function and the inverse sine function. So now we're going to just bring our calculator back, and let me clear that, and we're going to notice the inverse trig functions are going to be the second functions of the regular trig functions. Now this calculator actually is using a little bit of an older notation. Instead of writing sine -1 like this are, you know, in modern inverse notation, it's using the older inverse notation, which used to be called arc sine, right? So you see A cosine, A sine, A tangent. So it doesn't matter, but it's the same thing. When you see that A sine, that means inverse sine, like this. So we're going second, again, make sure you're in degree mode, which I already have made sure that I am. And then you're going to type in that number. So 0.95 95237612, right? Now remember, we're looking for an acute angle, right, which has this particular sign. There it is. Okay, so we get 72 approximate. So let's see if there's a rounding instruction. No rounding instruction is given, so we will just go to 2 decimal places. So 72.25. Okay, so theta is approximately 72.25. All right, so what does that mean? That means if I take the sine of this number, let's go ahead and be consistent, put our degrees on that. That is an angle. So if I take the sine, here's a quick check, right? If I take the sine of 72.25 degrees, I should get something very close to that number that we started with, right? And notice we do. Okay, it's not exactly the same. Why? Because we rounded, right? The more of those digits that I use in here, the closer I will get to that number that we started with. Okay, so but just to get you to understand what exactly we're doing here, that's a really good demonstration of what we did to obtain that result. All right, that's how you handle these. Okay, so now we want to find another acute angle that satisfies this particular condition. This time we want to provide an answer accurate to 5 decimal places. Make sure you're in degree mode, right? Now, you know that we're not ready to punch this in yet, right? Because as you recall, this is not a function, the secant is not one of the functions on a calculator. So what we're going to do is we're going to do a little bit of algebra first. We're going to replace secant of theta with 1 over cosine theta, right? That's going to be approximately 1.0692. So if I cross multiply, I end up with 1.0692 times cosine of theta equals, remember you can put a 1 down there, 1. So cosine of theta is going to be 1 over 1.0692. Now I did all that work because I wanted you to see it at least once why this happens. But normally when you see this, you can jump directly to this. You can say, oh, since the secant of theta is that, the cosine of theta is just the reciprocal of that, 1 over 1.0692. So we can really skip all that now that we understand that relationship. Remember, secant of theta equals 1 over cosine theta, and cosine of theta is equal to 1 over secant of theta as well. Okay, so now let's go over here. So we have cosine of theta equals 1 over 1.0692. So the same kind of relationship that we discussed with inverse functions for sine work for cosine as well. So in other words, if cosine of theta equals a, that's equivalent to saying that the inverse cosine of a equals theta, right? So here when I want to find theta, I just need to do the inverse cosine of that fraction, 1 over 1.0692. So, and we're going to go to 5 decimal places. So let's go ahead and bring back our calculator. So we're going to do second cosine. That just means inverse cosine, arc cosine of 1 divided by 1.0692. Okay, make sure you type it in correctly, 1.0692. all right, now we hit enter. There's our angle. Okay, So theta is, we're going to go 20.72678. 72678. And that's in degrees, of course. Okay, let's make sure we type that correctly. 20.72678. Okay, just like that. So remember, when it comes to these functions that are not represented on the calculator, you need to first do some work and turn it into one function that is on the calculator, then proceed to find the angle. So here's a question that is testing to see whether you understand the relationship between a trig function and its inverse. All right, remember we said if cosine of theta equals a, that's equivalent to saying that the inverse cosine of a equals theta, right? So if I want to get the a that did this, basically I would want to find the cosine of this angle, right? So in other words, here we're given inverse cosine of a equals 56. Remember, that means this is going to be in degrees. So this implies that a is going to be the cosine of 56 degrees. So that's why it's so important to understand this inverse relationship. Then it becomes really simple for you. So you know that you would have to type cosine of 56 to obtain the answer that you want, right? So we want 7 decimal places, so 0.5591929. 5591929. How many places is that? 2, 4, 6, 7. Okay. 0.5591929. Notice there's a 0 after that 9, so it stays at 9. Okay. That's what you would have to do. So here they're giving you the angle and they want to know what's the cosine, basically. So basically you're going to just type in cosine of 56 degrees and that'll be the answer there. Okay, make sure you understand that and then we'll proceed. All right, here's a problem that's slightly different because until now they've just said find one angle between 0 and 90. In other words, here we need to add in a degree to be consistent. Between 0 degrees and 90 degrees for which certain things happen, right? They give you some kind of a function value. Now here they're saying find all values of theta. So in other words, all angles, not just between 0 and 90, but going around an entire revolution, an entire cycle that satisfy this condition. So let's go ahead and bring up our calculator and get at least one angle. Now remember, sine of theta equals a is equivalent to saying that the inverse sine of a equals theta, right? So theta here is going to be the inverse sine of 0.40404. Now remember, when we find that, that's just one angle that satisfies this equation. There's more, there's in fact there are infinitely many angles that will satisfy it. But we only care about just finding the ones that are between 0 and 360 right now. So let's go ahead and compute the inverse sine, so shift sine of 0.40404, right? So notice that here we have one result. So 20, let's just go to 2 decimal places. So 23.83. So theta is approximately 23.83. Now, we're going to bring back our graphic to help us find any other ones that may exist. Okay, so notice that we have found one angle, which is quite small. It's around that much, right? So we found one angle here that satisfies this condition. But remember, this is not the only angle between 0 and 360 whose sine will be this result. There is one other. Where is it? Well, remember, we want the sine to be positive, and the only other quadrant between 0 and 360 where the sine is positive is right here. So this mirror image here, right there, this other angle, so if I call this one, let's call this one theta 1, and we'll call this one theta 2. So notice that this other angle will have the exact same sine as this angle, right? So the only question is, how do we find out what that is? Well, remember, we know that whatever this acute angle here is, that's going to be the same acute angle. So to get what theta 2 is, we can take 180 and subtract from it 23.83. Don't forget there's degrees there. So 180 degrees minus that, that's going to give us the second angle within the interval 0 to 360 inclusive, which will have that sine. So if I just do 180 minus 23.83, I get 156.17. So 156.17 degrees. So this is the other angle whose sine should be approximately this. Let's test it. All right, we know that. So let's go ahead and test actually our first result itself. So sine of 23.83. Now, do I expect to get exactly this number when I punch it in? Of course not, because I know there's rounding involved, right? But I do expect to be close to it. And notice we are extremely close to it, okay? So let's go ahead and check 156.17 degrees as well. And of course, we get exactly the same sine, right? So this is how you go about doing this when they ask you for not just the first acute result, which is what the calculator is going to provide, but also any other results from your understanding of the trigonometric functions. All right, finally, we're going to look at a couple of applications involving angles which we cannot find without a calculator, and that should do it for today. All right, so in this example, we notice that when an automobile travels uphill or downhill, right, on a highway, it experiences a force due to gravity. This force F in pounds is the grade resistance and is modeled by the equation F equals W sine theta, where theta is the grade and W is the weight of the automobile. So notice here we have the theta as the grade, and it's a positive angle when you're going uphill, and the grade will be considered to be this negative angle when you're going downhill. And let's see if we can answer some questions now based on this force. So here we're going to calculate the force to the nearest 10 pounds for a 3,000 pound car traveling an uphill grade with theta equals 3 degrees. Let's bring our formula to take a look at real quickly. All right, so remember that we use this formula, and this is our scenario. We're going uphill, so theta is greater than 0. It's at exactly 3 degrees. So all we have to do is really substitute. So we get equals, F equals W, which is the weight, 3,000 times sine of 3 degrees. And we go ahead and get an approximate value for it. All right, so we get 3,000 sine of 3 degrees. Of course, as always, make sure that you are in degree mode. All right, so we get 157. Let's just go ahead and round to the nearest 1. All right, so approximately 157 pounds. Actually, I take that back. We said to the nearest 10 pounds. So to the nearest 10 pounds, it's actually approximately 160, correct? All right, so let's go ahead and figure this next one as well. Calculate F to the nearest 10 pounds for a 6,000 pound truck traveling a downhill grade with theta equals -3 degrees. Of course, we don't have a truck here. Just imagine that's a truck. So we get 6,000 this time times sine of -3 degrees. So here we end up with 6,000 sine of -3. Okay. -314, and to the nearest 10 pounds, that's -310, right? So approximately -310 pounds. All right, so it's kind of interesting to think of what it is we're actually finding, right? So one way of thinking about this force is the fact that, let's say you want this car to stop here, right? Just it's on an incline and you need to park or something, right? Well, this would be the force that your brakes would have to overcome so that the car doesn't just roll back, right? Or if you're interested in what it means as far as motion is concerned, at any instant your car has to apply more than this amount of force in order for it to be able to go upward, right? Or to propel on its path. In the same manner here, let's say this truck is stopped here, right? Then it'll have to overcome this kind of a force so that it doesn't roll down. Or if for some reason you need to go backwards, you would have to overcome that to be able to go, say, in the reverse direction. All right, so this provides us with a nice example of, trigonometric functions in real life. Let's look at one more example and we'll call it a day. Actually, we need to quickly finish two other parts for this problem, which are two special cases. One is when the angle theta is 0. The other is when the angle theta is 90 degrees. So for the first part, 0 degrees, we know that the force F is given by W sine theta. So we're going to use the weight of the car, which was 3,000 pounds, times the sine of 0 degrees. Now 0 degrees, as you know, falls right here. So basically, if I just pick this point to be 1, 0, the x is going to be 1 and the y is going to be 0, and of course r is the distance between the origin and the point that we've picked on the terminal side of the angle, which is going to be 1. So therefore the sine of 0 will be y, which is 0 over 1, which is 0. So this is really, because of the fact that this part will be 0, the product will end up being 0, which makes sense, because if there's no angle, gravity isn't going to be pulling the side or putting any force on the car that would move it at all. So it's just going to sit there on flat ground. Now, in the next extreme example, if the car is in a situation which is going straight up, for instance, right? Notice gravity will be putting quite a bit of force on it. In fact, the entire weight of the car, that's the force the car will have to overcome if it wants to move that way, right? So let's see what the force will be in that case. We have F equals W sine theta, and it's going to make sense because if you recall, here we have sine of 90 degrees. Now 90 degrees is right here, so if we pick this point, so this is our 90-degree angle, right? So if we pick that point as 0, 1, 0 will be x, y will be 1. So you know that the sine of 90 degrees is going to be y over r. R again is the radius of the same circle, so it's also 1. So we get 1 over 1, which is 1. So here we get 3,000 pounds times 1, which of course ends up being 3,000 pounds, which again makes complete sense, because if your car is going straight up, the entire weight of the car is going to be pulled down by gravity. All right, so there is that, and now we'll really just do one more example and that'll be it. Okay. All right, this truly is our last example, and here we have a car traveling on a 2.5 degree uphill grade with a grade resistance of 120 pounds. We want to determine the weight of the car to the nearest 100 pounds. Now, this time they're giving you the resistance. So remember the formula, F equals W sine theta. What's given this time is F and theta. What is wanted is W. So let's substitute, or what we could do actually, if you want to be algebraically more sophisticated, solve for W first, then substitute. To solve for W, we're going to divide both sides by sine theta. So we get W is equal to F over sine theta. So we get W is equal to 120 over sine of 2.5 degrees. All we have to do now is go ahead and plug that in. So 120, make sure of course you're in degree mode, divided by sine of 2. That's 2.5. Let me make sure that's more clear. 2.5, and we end up with 2,751 to the nearest 100 pounds. So that's 1/1000. So notice there's a 5 to the right, so we have to round up. So 2,800, approximately 2,800 pounds is the weight of a car in this scenario. All right, so another nice application for us. Go ahead and make sure that you don't fall behind on homework, and that should do it for this lesson. Stay safe till our next meeting.